Baby shark doo 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 doo, baby shark doo 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 doo, baby shark doo 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 doo, baby shark. Just kidding, we're not going to do that. We are going to move on. Just kidding. Principles of engineering. We are going to do activity 1.2.3 electrical circuit simulation. There is a separate video that goes over how to do the assignment. However, this is the presentation, so if you need to follow along, I recommend you have notes and you have a calculator. We're going to go and open up that PowerPoint. I already got it going right here. And then from the beginning. So to start, what is electricity? Electricity is the movement of electrons. It's invisible, obviously. Produces light, heat, sound, and motion. Typically, we will use it when talking about its use in this class is to provide power. All right. Now, to understand where we're going, we need to break it down to its simplest forms. And the simplest form of matter is elements. So here's your periodic table. You got your hydrogen, lithium, helium, all your other ones, carbon, nitrogen, oxygen, and copper, nickel, zinc, and I'm just trying to see how much I remember of the periodic table, but we just need to know that because these atomic numbers will help us later on, as well as knowing how many valence electrons would allow us to determine whether an element is going to be conductive or an insulator. So we have atoms, and those are the smallest piece of an element, and those contain all the properties of that element. So here's an example atom. You got protons and neutrons within the nucleus being the center point of the atom. What you see there, right there. All right, the protons are positively charged, hence the pro, if you can't remember that. Neutrons are neutral, so they're uncharged. The atomic number is equal to the number of protons in the nucleus. So in this example, we have 1, 2, 3, 4 protons, so the atomic number would be 4. And we would be able to determine what type of element that is just off of that information. Okay, we also have electrons. Electrons are negatively charged particles that go around in different orbits. And typically, this is a version that you'll see, but when we will draw them, you have 3D versions and 2D versions. So we're gonna just do circle, 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 so on, to represent the electron orbitals. All right, and the electron orbitals are the orbits in which the electrons move around the nucleus. Okay, the valence electrons, and this is the important part and why we're in here, is the valence electrons are on the outermost ring of an atom, and those determine whether an item is either a conductor or an insulator. And there's different ways to represent a electron. Or an element, sorry. There's different ways to represent an element. So the way that we're using is the Bohr model. There's also the electron cloud model, which is a more realistic version of how it would look, right, if we could see down to that scale and things like that. And then you have the quantum mechanics model, which is a mathematical model of electrons. So you don't need to know how all these work. It's just you need to know that there are different types and each type is used for different things. So how do we understand and describe what can't be seen? It's important to note that each model can be useful in describing properties, but not completely accurate based off our most current understanding. So that's the reason for the Bohr model, is just to kind of help us figure out the valence electrons. So when you get into chemistry, you'll get into using these models and graphs to be able to determine different electron configurations, but we're not getting into this at this class. It's just a little fun fact knowledge. Here we are getting into, and this is to figure out electron orbits based off of how many orbits there are. So if there is only one orbit around an element, okay, to find the maximum number of electrons, all right, in an orbit, it is a simple formula, 2n squared. All right, n stands for the orbit number. So we have, for example, one orbit. 1 squared is 1. 2 times 1 is 2. Boom. 2 electrons. Orbit number 2. 2 squared is 4. 4 times 2 is 8. Okay. 3 squared is 9. 9 times 2 is 18. 4 squared is 16. 16 times 2 is 32. 5 squared is 25. 25 times 2 is 50. 6 squared is 36. And 36 times 2 is 72. And then in our valence orbit, okay, you can never have more than 8. Doesn't matter how many orbits there are. There could be 72,000 orbits, and you can't have more than 8. And you can't have less than 0, but we know that because there's not anything less than 0. All right, the reason we bring that up is, once again, the number of valence electrons determine an element's ability to either conduct or insulate. So here we have copper. Copper has 1 valence electron, and electron orbits like to either have a filled ring or empty rings. All right, so how many electrons are in the valence orbit? For here, like I said, there's 1. Copper is a conductor. We know that. All right, so you're looking at, on the lower scale, it's going to be more conductive. The higher the number of valence electrons, the more insulative. For example, we have sulfur here. There are 6 valence electrons, and that's closer to 8, so it is a conductor. Electron flow is where an electron from one orbit can knock out an electron from another orbit. So this little green dot, if you watch real close, I'll have a nice demonstration. Comes in, knocks the other one, hits it out of the park, home run. When an atom loses an electron, all right, so when we lose this electron, it seeks to fill it with another vacancy. And so these electrons are moving from element to element. So electron flow, here's a demonstration. So you got, let's say this is copper. Copper, 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 copper. Electricity is created by the electrons that collide and transfer on these valence electrons out here. So playing your animation for you. Do it again. All right, very good. So we have conductors and insulators. Put this information out here for you. Conductors are where electrons can flow easily. Insulators where electrons cannot. Conductors have 1 to 3 valence electrons. Insulators have 5 to 8 valence electrons. Conductors include your examples, more metallic things: silver, copper, gold, aluminum, mica, glass, quartz. All right, not that rubber is an element, but rubber would be something that is an insulator. So for example, we have here, conductor would be like the tip of the needle nose pliers, the wires themselves. Okay, and then the insulators would be like the handle of the needle nose pliers and all the rubber that is around the wires as they're going. So that's enough to get us through the introductory terms, why electrons flow the way they do, what determines an element's ability to either conduct or insulate. So now let's talk about the electrical circuit itself. So how can we calculate voltage, current, and resistance? To start, we got to know what all these are. So volts is voltage, represented by the letter V. Current is amps, represented by the letter A. And resistance is ohms, represented by this horseshoe symbol. All right. I think it's omega. I'm not the best at Greek alphabet or anything, so I might be wrong, but it's the horseshoe symbol. To start, current, all right, and I like to show how electricity works using water. You don't want to ever mix the two, but as a plumber, this makes more sense to me to just get the ideas out there. Current is the flow of electric charge. So here we have a water tank. The pipe is filled with water. There's a faucet. And when that faucet is off, is there flow? No, there is no flow. All right. The water is sitting here in the tank. It's sitting in the pipe, but it can't go anywhere. So there's no flow. All right. When we open the faucet, now there is flow. So you can't measure current unless there is some sort of a power attached and that there's actually flow going through it. Otherwise, there is no current. There has to be flow. Here's an electrical example instead of the water. So battery hooked up to a switch. When the switch is off, there's no flow, no power, right? When the switch is on, there is flow, okay? Easy peasy. Before we get into voltage and resistance, you guys need to know that there are two different ways to represent current flow. We have conventional current and we have electron flow. Conventional is where your positive flows to the negative, and that's how we've typically thought about it in the past. But what actually happens is that the negative flows to the positive. So the negative comes up the negative side of the battery and flows to the positive. And let me get a battery and I'll just give a visual representation of that. Alright, so here's a battery now. Oops, sorry. Okay, this is the positive side of the battery. It's got the peg on it. Okay, and here is the flat side of the battery. That's the negative side of the battery. So typically we have thought that electricity would flow out of the positive to the negative, but in reality it actually goes from the negative to the positive. Now, engineering versus science, the reason we bring this up is that you're going to see this two different ways probably, especially if you get into different science classes. All right, engineering, and I don't know why the rule is this, but it is the way it is, so that way you know. Typically in engineering fields, we use conventional current, all right? Whereas in science, they typically use electron flow. So you need to know that both exist, but in this class, and most likely in other engineering classes, you are going to use conventional current. So now that we've done current, let's get on to voltage. Voltage is the force pressure, the pressure that causes the current to flow. So if this was current, not voltage, right? If this was current, the faucet is off, there is no current, all right? Voltage, however, is pressure. So there's water sitting in this tank, and obviously gravity pushing down on the water, and the water's pushing out on the pipes. So there is pressure. Whether the faucet is on or off, there is still pressure. So you can measure volts. So voltage is the pressure, current is the flow. So right now, there's pressure. We open the faucet, and guess what? Yes, there still is pressure. Once again, still pressure. And now there's pressure still. All right, resistance is the opposition to current flow. So this is measured in ohms. So here's a little demonstration. When we drop a rock into our tank, it goes down the pipe and it gets stuck in the faucet. All right, that is going to cause resistance, reducing the amount of flow. So a resistor just allows us to take some energy, and it pretty much, it will adapt the voltage and amperage, which you'll see later on. But if you need a light to only get so much power from a source because you don't want it to blow up or explode, or like a little diode will pop, literally, all right, then you will need that. So resistor, we drop it in, here's our light, the resistor gets dropped into our circuit. Now the light doesn't provide as much. Now measuring voltage, we got to talk about how to use a multimeter. All right. If you don't use it correctly, you're going to blow the fuses in it. And that's why for this lesson, while I'm not here, so we don't ruin a bunch of stuff and keeping track of it, there's a simulation that we'll use instead. But for real life, you need to know how to use a multimeter. And the first rule is to always start larger and go backwards. So if we look at this, all right, it is on 20. All right, working with a 12-volt battery, we know that nothing's going to be over 20. So we start large and then go small. We don't want to start down here. We don't want to start down here and then go up. If we start too low, we might blow the fuse when we connect it. So we start large and then go small until we start to get a reading. So when measuring voltage, we measure across a component. All right. So when we measure across a component, that is where we take our leads, the positive and the negative, and to figure out the voltage at the battery, say, all right, we should plug this, we would attach it to the battery here, and the battery there, or the wire on one side and the wire on the other. And that would tell us the voltage at the battery. Same thing for the switch, same thing for the resistor, same thing for the light. So you have to measure across to the component. All right, it's not too much of an issue if you accidentally flip these and do like one, you're just gonna get a negative reading. All right. An instrument used to measure the properties of an electrical circuit, that's the multimeter. So you can measure voltage, current, and resistance, or volts, amps, and ohms. So measuring current is different than measuring voltage. Once again, we start large on our reading and then go down so we don't blow the fuse. Circuit flow must go through the meter though. So we're going to remove that wire, take it out of the equation, and we would literally have the electricity flow through the switch into the multimeter, out the other lead of the multimeter, and into the resistor. And that allows us to measure the current at each location. Okay. So then you would do the same for like switch to resistor, resistor to light, light to battery, battery to switch. Okay. Measuring resistance is just going to be like voltage. Once again, we make sure that the knob on the dial, or the dial is to the correct location, start high, go low. And just like voltage, we will measure, but the only difference is now we don't have the battery. All right, do not have the battery. Repeat, do not have battery, bad. Okay, so you have to take the power out of it to measure the resistance. And you measure just like voltage across the component. So the resistance at the switch, the resistance at the resistor, the resistance at the light, and the resistance, you could do the resistance at the battery, but I wouldn't recommend it. So what we're gonna do now is make sure you got your notes all good. I'm gonna stop this video. I'm gonna make a part 2 video, and for part 2, we will continue on from this page on to do some circuit calculations. So with that, if you have any questions, let me know. If I'm available, I will get back to you via email. If I'm not, I apologize. Once again, it just depends on what I'm gone for. But make sure you talk to your sub, talk to your other students, and some good other good resources would be talk to the EDD students, since they have already done this last year or the year before. So with that, toodles y'all.